Okay, so picking up where we left off, we are now going to move into the direct comparison test, which if I had a favorite test, I think this has got to be it. Because once you get used to sequences and series, you start realizing that you don't have to do all these tests all the time. You just have to think about, all right, how big is this series? So the direct comparison test basically says something that, if you really think about it, is common sense. Now, when I say common sense, I mean common sense for a calculus student, not for my algebra kids, but even close, this is common sense for like an algebra kiddo. The direct comparison test says if something is smaller than a convergent series, and it's already written here, so you don't need to write this, you would have to converge. Because if something is smaller than a convergent series, that means the first one was small enough to converge, and this is smaller than that, excuse the bell behind me, then that means if I've got another one that diverges, that must mean that if I'm bigger than a divergent series, I would have to diverge by the same logic. So if the first one's already too big to converge, and another one's bigger than that, then it's too big to converge. Now, what's tricky is make sure you don't mess around in between. If you're smaller than a divergent series, I don't know what you do. And if you're bigger than a convergent series, I don't know what you do. And you have to have some further inspection, okay? So here's how it works in practicality here, is if I look at this thing, it looks like a big nasty, oh goodness, if only that were a p-series, if only this said, find the summation of 1 over n squared. Well, it kind of does. Because with this addition of 3n plus 4 on the bottom, what that's really done is, it's made the bottom part bigger, which makes the values in that fraction smaller overall, because if I have a bigger denominator, I have a smaller value overall. So my series is smaller than 1 over n squared. 1 over n squared is a p-series where p is greater than 1, so this converges. Therefore, since this is smaller than the convergent series, this converges too. And if I look at this guy, oh, e to the n over n plus 1. Well, what if this just said 1 over n plus 1? That's a lot like a p-series. In fact, it's just a p-series shifted over a term. So this is a p-series, and then I have e to the n over n plus 1. So that's going to be bigger. This guy is basically a p-series where p equals 1. Well, if p equals 1, that diverges because it makes it like a harmonic. And this is bigger than that, so it has to diverge too. The other reason this diverges is if I have e to the n over n plus 1 and I take the limit as n approaches infinity, that's going to be infinity over infinity. And then when I do L'Hopital, I end up with e to the n over 1, which is infinite. This diverges because it doesn't pass the nth term test. And then last but not least, example 3 converges because I have 1 over n squared, and then I make the denominator bigger by multiplying by ln n. So this converges because it's smaller than 1 over n squared, and 1 over n squared converges. All right, the next one's the limit comparison test, and I gotta be honest, we don't use this one a lot because most of the time we can do this with the direct comparison test instead. All right, so here's what the limit comparison test says. It says if the summation of a sub n and the summation of b sub n are positive term series, if you take the limit of the ratio of those two general terms and you get a value between but not including 0 and infinity, then both series converge or both series diverge. Here's what this is basically saying. It's saying, let's say you get one of those ambiguous cases where you're bigger than a convergent series or smaller than a divergent series and you don't know what else to do. Instead of just comparing them, divide them and see what happens. So let me give you an example here. I've got 2n plus 1 over n plus 1 squared. So this is bigger than 1 over n plus 1 squared. And 1 over n plus 1 squared converges because it would be like a p-series that converges. So I'm bigger than a convergent series. Okay, fine. But I don't know what that means. Bigger than convergence could kind of go either way. So what we do is we say, well, I'm going to compare this to 1 over n plus 1 squared, which I know converges. So I'm going to take the limit as n approaches infinity of one of these divided by the other one, and it does not matter what order you go in. It's just one divided by the other in any order you want. So I'm going to take the limit of 2n plus 1 over n plus 1 squared times n plus 1 squared over 1. And then I'm going to get the limit as n approaches infinity of 2n plus 1, which equals infinity. Darn it. Well, that was problematic, and I did this so you could see what happens here. I got infinity. I only know things if I get a limit between 0 and infinity. So I need to kind of think about something else here. So let's think of something else that I know about. Well, let's see. You know what else I know about? I know about the summation of 1 over n, and that diverges. So I'm going to try and take now the limit as n approaches infinity of 2n plus 1 over n plus 1 squared times the reciprocal of 1 over n. So this is going to be the limit as n approaches infinity of 2n squared plus n over n squared plus 2n plus 1. And as n goes to infinity, these are both polynomials. I can take their ratio and get 2. 2 is a number. Since the limit equals a number, that means the two series that I was dividing were doing the same thing. And they were doing the same thing, which was diverging. So the limit comparison test is there for you to say, wait a minute, that direct comparison test didn't really help me, but I know what to compare it to. So instead of just saying, well, what's it bigger or smaller than, just say, well, I know 1 over n diverges. How about I divide the two and see if I can get a number? If I get infinity, I have to try again. If I get a number, I can stop and say whatever the thing I was comparing it to did, my series does. This diverges. All right, 1 over 2 to the n minus 1. So the reason I put this one in here is I can compare it to 1 over 2 to the n. 1 over 2 to the n, if you write it out, starting at n equals 1, would be a half, a fourth, an eighth, a 16th. That would be geometric. But I'm subtracting 1 from the bottom, so I would have 1, a third, a seventh. And that seems a little weird. Like that's technically bigger than a convergent series. Bigger than a convergent series is ambiguous. So I say, all right, the thing I compared it to, instead of just directly comparing them, I'm going to divide them. And I'm going to say take the limit as n approaches infinity of the first guy times the reciprocal of the second guy. So I have the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. That's going to go to infinity over infinity, so I do L'Hopital, and it's the limit as n approaches infinity. The derivative of 2 to the n is 2 to the n ln 2. 2 to the n ln 2. Oh, okay, now I get 1. 1 is between 0 and infinity, so these two things did the same thing. This converged because it was geometric and r is less than 1. Therefore, this converges. Okay, it's a little abstract, but hopefully you kind of followed along there. All right, I'm at 9 minutes. I'm doing great here. And then last but not least is the ratio test. And the ratio test is basically if you have factorials, this is the way to go. So if I have a series that's got a boatload of factorials or a boatload of exponentials in it, this is the way to go. The ratio test basically says you're going to take the ratio test just like we did before when we were finding the interval of convergence, except when I get to a point where before we had like x over 3 when we were finished, I'm not going to get x over 3. I'm just going to get a number. Okay, so this ratio test is just like the other ratio test we did, except the x's are now gone. So the ratio test is great for factorials, great for exponentials, and the ratio test says basically take the limit as n approaches infinity of the n plus 1th term divided by the nth term, and your series will converge if you get a value less than 1. It'll diverge if you get something greater than 1, and then you don't know what happens if it equals 1. You have to go and do something else. All right, so if I look at this guy, whoa, look at that big weird series. I have no idea what that does. Well, I know what that does, but you don't know what that does. So, gosh, direct comparison test? No way. I don't know how to directly compare with factorials. That's crazy. And I couldn't do the ratio, not the ratio test, the one we just did, the limit comparison test, because again, I don't know what to directly compare this with, because it's got factorials, and factorials are weird. So if I want to know what this guy does, I'm going to do the ratio test. I'm going to take the limit as n approaches infinity of a sub n plus 1 times the reciprocal of a sub n. And notice there's no x's here to worry about. And now we come to my favorite part, which is canceling here. So I'm now going to cancel. These 3 factorials are gone. N factorial is 1 less than n plus 1 factorial, so it really just leaves n plus 1. 3 to the n plus 1 has 1 more 3 than 3 to the n. And n plus 3 factorial is 1 less than n plus 4 factorial. So this really gives me the limit as n approaches infinity of n plus 4 over 3n plus 1. And if I take the limit as n approaches infinity of a rational function like this, it's the ratio of the coefficients when the degrees match, which is a third. A third is less than 1. This converges. Okay. And then I come over here and I think, okay, wow, what does this one do? Now let's pretend for a second that you didn't know this one was part of the ratio test, and you just were asked on an exam, hey, what does this numerical series do? Does it converge or diverge? Let's go through all the steps. So step 1 is the nth term test for divergence. So step 1 is just take the limit as n approaches infinity of this guy. Well, that's going to be infinity over infinity. That's not helpful. So now I'm going to do L'Hopital here. The first times the derivative of the second plus the second times the derivative of the first. 2 to the n ln n. Okay. So then these guys basically cancel. And I have the limit as n approaches infinity of 1 plus ln n over 2 to the n ln 2. This should say 2, not n. Plug in infinity. Ugh, infinity over infinity. Okay, L'Hopital, one more time, and then I'm done with you. Limit n approaches infinity. Derivative of ln n is 1 over n. This down here is going to become 2 to the n ln 2 squared. Now as n approaches infinity, this is going to 0 divided by infinity, which is going to be 0. Okay, so that tells me my terms go to 0. Hooray! You have passed the first hurdle. You might converge, but I have no idea if you do or not. Darn it. Okay, so next. If I look at this, maybe a direct comparison test. This isn't a p-series. It's definitely not harmonic. This 2 to the n, though, if this were 1 over 2 to the n, that would converge, right? Because that would be a geometric series. So I'd say, okay, I could maybe compare this to that. So let's see if it works. A direct comparison test with a convergent series, except my numerator is bigger than that one. So I'm bigger than a convergent series. So the direct comparison test has failed me. Bigger than converging is ambiguous. Darn it. Okay, so now at least I knew what to compare it to. So now let's do the limit comparison test. I'm going to take the limit as n approaches infinity of the one I have divided by the one I know about. Okay, that's, say, 2 to the n over 1, pardon me. Cancel, cancel, but as n goes to infinity, this is infinity. And the limit comparison test said you need to get a number between 0 and infinity, and I didn't. So my limit comparison test didn't really help me. See what I mean? All my tests have failed me, so I need a new test. In comes the ratio test to help out. Dun, da, da, da. You have a factorial, let me cancel it for you, is what the ratio test says. So I'm now going to do the ratio test, which says take another limit, but this time take the limit of a sub n plus 1 divided by a sub n. And then see what happens. All right, so cancel, cancel. Nobody else really cancels, so I have the limit as n approaches infinity of n plus 1 ln n plus 1 over n ln n. Ugh, this is most definitely not very fun here. Well, what do I want to do next? So I have that as n approaches infinity. I get infinity over infinity. L'Hopital, you little stinker. I need you again. Alright, so I have the first times the derivative of the second. Ooh, I like this. Plus the second times the derivative of the first. And the first times the derivative of the second. Plus the second times the derivative of the first. Oh goodness, is everybody bored yet? I'm pretty bored. How's everybody's day? You having a good day so far? My day was good, Mrs. Vibber, and then I started this video, which is now 17 minutes long. Hurry up! Yes, I heard you. I heard you. We're almost there. So now with L'Hopital, these guys cancel, and I have 1 plus ln n plus 1 over 1 plus ln n. Okay, I'm almost there. I still have infinity over infinity, but the next derivative should be all I need. Do I have enough room? Do I have enough room? I do. So now I'm going to take the limit as n approaches infinity after one more L'Hopital, which would be 1 over n plus 1, divided by 1 over n, which is the limit as n approaches infinity after a simplification of n over n plus 1, which is, hallelujah, 1, 1. Ugh. Is inconclusive. Ratio test, you failed me. You failed me, you failed me, you stinker. Now what am I supposed to do? Well, you know what I'm supposed to do now? I'm supposed to do this next guy. And I'm going to stop there, though, because it's 18 minutes of chaos. So I guess my last joke, which I don't know if I've used before, but it's worth saying again. What kind of shoes does a ninja wear? What kind of shoes does a ninja wear? They wear sneakers. You know, because they're sneaky. They wear sneakers. Okay, I'm all done now. See you later. Bye.